Have you ever wondered why a bridge doesn't just fall down? Or why your smartphone screen can survive a small drop but shatters from another? Collage of everyday objects. Bicycle, smartphone, bridge, cooking pan. It's all materials. It all comes down to materials. Engineers and scientists spend a lot of time testing these materials. Why? Because we want to build things that are safe, strong, and last a long time. We can't just guess that a certain metal is strong enough for an airplane wing. We have to know. Testing is how we get the facts. It's like being a detective for the physical world, gathering clues to understand how a material will act under pressure. Before a chef creates a new dish, they taste all the ingredients. Sweet, salty, how they'll combine. Material science is a lot like that. We poke pull press to understand their flavors, their properties. Understanding these characteristics leads to innovation. Let's talk about mechanical properties. That sounds complicated, but it's not. It's just a fancy way of describing how a material responds when you push or pull on it. Think about a piece of chewing gum. You can stretch it really far before it snaps. That's a mechanical property called ductility. Now think about a glass cup. If you drop it, it shatters into a million pieces without stretching at all. That's called being brittle. Strength, hardness, flexibility. They are the personality traits of a material, telling us its story when forces are applied. One of the most common tests we do is the tensile test. Imagine you have a dog bone-shaped piece of metal. Why that shape? The middle part is thinner, so we know exactly where it will start to stretch and eventually break. We put this sample into a big, powerful machine that pulls on both ends very, very slowly. A computer measures exactly how much force we're using and how much the material stretches. It's like a super-controlled game of tug-of-war. This test tells us the material's tensile strength, how hard you can pull before it breaks, and its ductility, or how much it can stretch. Next up is the hardness test. This one is simple to picture. It measures how well a material resists being scratched or dented. Think about how a diamond can scratch glass, but your fingernail can't. That's because a diamond is much, much harder. To test this, we take a very hard object, usually a tiny diamond or a metal ball called an indenter, and press it into the surface of our material with a very specific amount of force. Then, we measure the size of the tiny dent it leaves behind. A smaller dent means the material is harder. It's like poking your finger into a cake versus a brick. First up is the impact test. This test answers the question, what happens when I hit you really, really hard? Some materials that seem strong when you pull on them slowly might shatter if they get a sudden shock, especially when it's cold. To test this, we use a machine that's basically a giant pendulum. We take a small, notched bar of our material and whack. We measure how much energy the sample absorbed by seeing how high the pendulum swings up on the other side. A material that absorbs a lot of energy is considered tough. Then there's fatigue. Have you ever bent a paperclip back and forth until it suddenly snaps? That's fatigue. A material can break even when the force applied is way less than what it would take to break it in a single pull. It just gets tired from being loaded and unloaded over and over again. To test for this, we put a sample in a machine that repeatedly applies a smaller force. It might bend it, twist it, or pull on it, thousands or even millions of times. We count how many cycles it takes for the material to fail. This is super important for airplane wings, which flex with every bit of turbulence. Let's not forget about creep. Creep is what happens when a material slowly deforms over a long time while under stress, especially when it's hot. Imagine a heavy bookshelf. Over many years, the wooden shelves might start to sag in the middle under the weight of the books. That's creep. To test for it, we hang a weight on a material sample and often put it in a hot furnace. Then we just wait and measure. We carefully track how much it stretches over days, months, or even years. Looking inside, the world of microscopy. Testing tells us how a material behaves, but to understand why, we need to look inside. We need to see its microstructure, the arrangement of its internal features. Tiny crystals called grains. The simplest way to do this is with a light microscope, like the one you might have used in biology class, but for materials. First, we have to prepare the sample. We cut out a small piece, mount it in a plastic puck, and then grind and polish it until it's as smooth and shiny as a mirror. This is a really important step. After polishing, the surface is perfectly flat, but we still can't see the microstructure. Side-by-side polished surface and the same surface after etching, revealing a complex pattern of grains. To make it visible, we use a process called etching. We apply a mild acid or another chemical to the surface for a few seconds. This chemical attacks different parts of the microstructure at different rates. For example, it will eat away at the boundaries between the grains faster than the grains themselves. For an even closer look, we need more power. That brings us to electron microscopy. Instead of using light, these incredibly powerful microscopes use a beam of electrons to create an image. Because electrons have a much shorter wavelength than light, we can see things that are thousands of times smaller. There are two main types. A scanning electron microscope, or SEM, scans the surface of a sample, giving us amazing three-dimensional-like images of its texture. A transmission electron microscope, or TEM, shoots electrons right through an ultra-thin slice of the material, allowing us to see inside the grains, right down to the arrangement of atoms. One of the most powerful is X-ray diffraction, or XRD. Imagine you're at the beach and waves are coming into shore. When they pass through the narrow openings between rocks, they bend and spread out. XRD works on a similar principle, but with atoms. We shoot a beam of X-rays at our material. The atoms inside are arranged in a neat, repeating crystal lattice, like a perfectly organized jungle gym. As the X-rays hit this atomic jungle gym, they bounce off the layers of atoms and diffract, or spread out, in predictable patterns. A detector measures the angles and intensities of these diffracted X-rays. It's like seeing the specific pattern of shadows cast by the jungle gym. By analyzing this pattern, scientists can work backward to figure out the exact three-dimensional arrangement of the atoms in the crystal. Another amazing technique is Fourier transform infrared spectroscopy, or FTIR. This method helps us identify the types of chemical bonds within a molecule. Every chemical bond vibrates at a specific frequency, like the one between oxygen and hydrogen in a water molecule, like a tiny tuning fork. In FTIR, we shine a beam of infrared light, which is really just heat, through our sample. The molecules will absorb the light that has the exact same frequency as their bonds' vibrations. The machine measures which frequencies of light were absorbed and which passed through. The result is a spectrum, which looks like a graph with a bunch of peaks and valleys. Each peak corresponds to a specific type of chemical bond. It's like a chemical fingerprint for the material. If we see a peak at a certain spot, we can say, aha, this material has a carbon-oxygen double bond. This is incredibly useful for identifying plastics, oils, and other organic materials. Another way to understand materials is by looking at their surfaces. The surface is where a material interacts with the world, where corrosion starts, where paint sticks, and where electronic connections are made. We have special tools to analyze just the top few atomic layers. One is X-ray photoelectron spectroscopy, or XPS. In this technique, we hit the surface with X-rays, which knock electrons out of the atoms. We collect these electrons and measure their energy. The energy of a freed electron is like a name tag, telling us exactly which element it came from, like carbon, oxygen, silicon, and even what other atoms it was bonded to. Finally, for the ultimate surface analysis, there's secondary ion mass spectrometry, or SIMS. This technique is incredibly sensitive. It can detect elements that are present in parts per billion. In SIMS, we hit the surface with a beam of charged atoms, called ions. This impact is like a tiny atomic explosion, blasting a few atoms and molecules off the surface. These ejected particles are then sent into a detector that sorts them by their mass. It's like being able to weigh individual atoms. We can tell with amazing precision what elements are on the very top layer of a material. All these incredible tests, from pulling to heating to peeking at atoms, help us build a better, safer, and more advanced world.